All right, let's dive into one of the most powerful and honestly coolest ideas in all of computer science, graphs. You might not see them, but they are the invisible skeleton holding our entire digital world together. Everything from your social feed to the map on your phone.
So, have you ever wondered about this? You sign up for a new app, and boom, it's already suggesting people you went to high school with. It feels a little like magic, right? Well, it's not magic. It's actually the power of graph theory doing its thing.
And here's the best part. Behind all that mind-bending complexity is an idea that is so simple, so intuitive, you already get it. We're just going to put a name to it and give it some structure. First up, let's just take a look at how widespread this concept really is. I think you'll be surprised to find that graphs are hiding in plain sight in almost every piece of tech you use.
I mean, just think about it for a second. Google Maps, that's just a gigantic graph where the cities are points and the roads are the connections. Your social network, a massive graph of people connected by friendships. The internet itself is just a graph of computers linked by cables. Even in AI, we model problems as a graph of possible states and the transitions between them. They are quite literally everywhere.
Okay, so to really talk about graphs, we need to be on the same page with the vocabulary. But don't worry, there are really only two main parts you need to know, and they're incredibly simple. First, we've got the vertex. You're also going to hear this called a node. They mean the exact same thing. This is just a single dot, a single entity. It could be a person, a city, a website. It's the thing in our network.
And second, we have the edge. This is the good stuff. This is the relationship, the line that connects two vertices. So if the vertices are the cities, the edges are the roads. If vertices are people, edges are the friendships. It's the edges that give a graph all of its structure and all of its power.
Now, this is a super important distinction. An edge can be a two-way street, what we call undirected. Think of a Facebook friendship. If you're friends with me, I'm friends with you. Or it can be a one-way street, or directed. Think about Twitter or Instagram. I can follow someone without them following me back. This one little difference, it changes everything about how you analyze the network.
Okay, so we've got this beautiful abstract idea. Dots and lines, nodes and connections. That's great, but how do we actually get that inside a computer? That right there is the core challenge.
Right, how do we take this sort of messy, beautiful spider web of connections and turn it into a data structure? Something a programming language can actually understand and work with efficiently.
And that brings us to a classic showdown in computer science. There are two main ways people do this, and they each come with some pretty big pros and cons. So let's put them head to head.
In this corner, we have the adjacency matrix. The idea is wonderfully simple. You just create a big grid, like a spreadsheet. You list every single node across the top and every single node down the side. Then you just put a 1 in the box if there's a connection and a 0 if there isn't. That's it.
And this shows you exactly how it works. So in this little graph, node 0 is connected to 1 and 2. So if you look at row 0, you see a 1 in column 1 and a 1 in column 2. Easy. And checking if two nodes are connected is super fast. You just look up one coordinate in the grid.
But here is the massive killer drawback. The size of this matrix is based on the number of vertices squared. We call that O of V squared. Now think about that. For a social network with 1 million users, 1 million squared is 1 trillion. You'd need a grid with 1 trillion cells, even if each person only has, say, 200 friends. Almost that entire grid would be filled with zeros. What a colossal waste of memory.
So that brings us to our second contender, the adjacency list. Now, instead of a giant grid for every possible connection, this approach is way smarter. It just says, hey, for each node, let's just keep a simple list of the actual nodes it's connected to.
Look at this. It's the exact same graph as before. But instead of that 3x3 grid, we just store that node 0 connects to 1 and 2. Node 1 connects to 0, and so on. There's no wasted space. It's just the essential information, nothing more.
And here is the key, the absolute magic of this approach. The memory it uses scales with the number of vertices plus the number of edges. We call this O of V plus E. This means its size grows based on how much stuff you actually have, not all the stuff you could possibly have. For what we call a sparse graph, like a social network with tons of users, but where each user only has a few hundred friends, this is a total game changer. It is wildly more efficient.
So the final verdict is pretty clear, right? While the adjacency matrix has its place for really dense graphs, where almost everything is connected to everything else,
The vast majority of real-world problems use sparse graphs, and for those, the adjacency list is the undisputed champion.
Okay, with the adjacency list as our winner for most situations, let's get practical. How would you actually start building one of these from scratch?
This right here is a really common pattern, especially if you're using a language like C++. Let's just walk through it. First, you read in the totals. How many vertices and how many edges are we dealing with? Next, you create the actual adjacency list data structure. Then, you just loop, reading in each connection one by one. For each of those, you add it to the list. And here's the key detail. If your graph is undirected, if it's a two-way street, you have to remember to add the connection in both directions to really represent that relationship.
And this really gets to the heart of the whole thing. The reason we use graphs isn't just to store a bunch of disconnected facts. It's to explicitly map out the rich, complex web of relationships between all of those facts. That's their real purpose.
So now you've got the fundamental building blocks. You know the what, you know the why, and you know the how. This structure is the starting point for everything. Finding the shortest path in Google Maps, spotting communities and social networks, solving countless problems. So the only question left is, what will you build with